Hello, please welcome Chris Richardson.
Hi. Great, thank you. It's nice to see that not everyone is at the talks on generative AI, because that seems to be pretty popular. So welcome to my talk on deployment pipelines. When I was here, this is my, does this work? Yes. So last time I was at JFocus was right before COVID, right, 2020. And I gave a talk, The Geometry of Microservices, where I used 6 shapes as visual metaphors for key aspects of the microservice architecture. And one of those shapes was the success triangle. And that describes how the main goal, not the only goal, but the main goal of microservices is to accelerate software delivery, basically supporting DevOps and enabling an organizational structure that sort of implements the team topologies patterns. So it's really all about how to accelerate software delivery. And now, 4 years later, I'm back to talk about another shape. And this time it's a cylinder, which is the visual representation of a deployment pipeline, which is the path that changes take from the developer's laptop into production. So changes go, you do a git push, that goes to a code repository, that triggers a deployment pipeline that ultimately ends up deploying those changes into production. And the big idea is this deployment pipeline should be fast, it should be automated, because that really is an essential ingredient of rapid, frequent, and reliable delivery of software. So if you go back to the success triangle, it's all about teams practicing DevOps, which includes the continuous delivery, and there's just a stream of small changes flowing from their laptops into production through this very fast deployment pipeline. So I'm just going to talk about one possible way of designing a deployment pipeline. There's lots of sort of technology options. But before I do that, a little bit about me. Yes, there are in fact parts of the world where they are warm and sunny. So do not give up hope. I was actually in Australia 3 weeks ago when I took this. I've done a million things over the years. I worked on Lisp systems back in the late 80s, early 90s. And these days, pretty actually for the past 10 years or more, I've been pretty much focused on the microservice architecture. Wrote the book, Microservices Patterns, among other things. I've got the website, microservices.io, which I'm sure many of you visit. And these days, I just spend my time helping clients use the microservice architecture effectively through consulting and training. And just sort of one quick shameless plug, on Thursday and Friday, I'm doing a two-day workshop as sort of part of JFocus, and there's still room for you to sign up. Matthias told me to tell everyone that. So hope to see some of you there. Okay, so here's the agenda. Just going to kind of provide an overview of the deployment pipeline and sort of the automated mechanisms that it uses. And then I'm then going to talk about the test pyramid, which defines the testing strategies that you would use for the microservice architecture. And once again, the goal is really to sort of accelerate the deployment pipeline. You only have a certain budget within which to do testing, time budget, and you want a testing strategy that optimizes that while minimizing risk. And then I'm going to talk about some of the sort of Kubernetes specific aspects of the deployment pipeline to do with container images and Helm charts and YAML files, right, which just seem a big part of modern configuration these days. And then I'm going to, at the end, talk about, okay, so we've got this artifact, the package as a service. How do we get that quickly and safely into production? How do we actually update the production environment? Okay, so that's the agenda. Let's get going. So hopefully you can read this slide. So, as an example, I've got this Spring Boot-based service. It's using JPA. So it's persisting entities in a Postgres database. It's also subscribing to events, or actually more generally messages, via Kafka. Interestingly, because it's using the transaction outbox pattern, it doesn't actually publish messages directly to Kafka. They actually go via the outbox table and eventually end up in Kafka. So if you're wondering why it's just subscribing, that's why. And then it's using Spring Authorization Server to get the keys to authenticate JWTs, because it's obviously got a secure REST API. So typical Spring Boot microservice, and in fact, pretty much everything I'm talking about isn't, it could apply to services written in other languages as well. It's fairly sort of generic language-independent concepts. So then the big question mark is, what's the path from developer laptop to the production environment? So the old way of doing this, obviously, would involve like lots of manual handoffs, right? Where I'm a developer, I write code, and apparently I don't test it, so I throw it over the wall to the QA team. And then probably I have to go interact with the security team. There was one client I worked with many years ago. The developers had to email the class files to the security team where they would actually check it. So it just totally blew my mind. Hopefully none of you are doing that. And then ultimately it gets given to the ops team, who somehow update the production environment. Maybe they SSH into machines and copy files around. But that's sort of the old way. It's slow, it's manual, it's unreliable. So modern software development is really about fast, automated deployment. And kind of a key theme in this talk is all about fast feedback, all about shortening the feedback loops. So DevOps is most certainly all about automation. And then also one of the key aspects of DevOps is about feedback. And that includes feedback from the deployment pipeline and also from the production environment as well. And that feedback should clearly be fast. And then there's this really fascinating concept, which I read about last year. It's this formal three-dimensional model for the developer experience. And it's comprised of three components: flow, feedback, and cognitive load. And you want to minimize cognitive load, have fast feedback, and provide plenty of opportunities to flow. And all of that kind of relies on, sort of underpinning a lot of that is actually shortening feedback loops. So shortening the time between committing a change and getting feedback as to whether the test passed, and also shortening the time between that commit and actually having that change deployed into production. So that's sort of the big idea. It's all about automation plus fast feedback, or similarly short feedback loops. So you need an automated deployment pipeline that sort of looks like this. So you've got a Git repository that acts as the source of truth. All changes should flow through that. Developers are practicing continuous delivery, so they're committing to trunk, ideally multiple times a day. Each one of those changes is triggering the deployment pipeline that is building, testing, and then hopefully just automatically deploying the changes into production. So, and why not? Let's do it within 15 minutes, because that's, in a sense, that sort of echoes the XP 10-minute build, right? We want to have fast feedback. We don't want to sit around and wait and then have to context switch to remember what we were working on that broke in the deployment pipeline. So the actual deployment pipeline is, it consists of a series of stages. I mean, this is certainly one way of looking at it, right? It obviously builds the application, although that's, in my opinion, sort of the minor part. The really interesting part is that it's executing a series of tests, and as you move from left to right, those tests tend to get slower and slower and slower because they're much more heavyweight. So you want to have the fast ones up front to minimize the feedback time. Now, in a microservice architecture, you'd actually have a deployment pipeline per service. One of the key defining characteristics of the microservice architecture is that services are independently deployable, that each one has its own has its own deployment pipeline, and it is tested in isolation. And so if you're doing end-to-end testing of your microservices, something is not quite right there. So that's sort of the big idea. And the specific deployment pipeline I'm going to talk about looks like this. And this is kind of a busy diagram. Hopefully, this is a big screen, so I think you can see it, right? So there's various different parts to this. So a developer would get on their laptop, would do a git commit and a push to the services code repository. That then triggers the service pipeline that has a test suite that's organized according to the test pyramid that I'm going to talk about next. And then the actual output of that part of the deployment pipeline is a container image, Docker container image, and what's known as a Helm chart, which is Kubernetes packaging format. Those two things get published to a container registry. So at this point, we've built the service, packaged it as built and tested the service, packaged it as a container image, and then published that image along with a Helm chart that's actually a bunch of Kubernetes template files into a repository. And then, in theory, in order to deploy that new version, we would make there's actually another repository that defines what is deployed in production. And so we will actually edit some manifest file within that to say, to deploy this new version of that Helm chart. And then there's tooling that is running inside the Kubernetes cluster to actually ensure that the desired state as defined by, or actually the actual state of the Kubernetes cluster matches the desired state as defined by the Git repository. So we're actually using a technique called GitOps here, where the Git repository defines what the desired state of the Kubernetes cluster is. And that step 3 sounds a bit tedious, and later on I'll show how you can actually automate that as well. So anyway, that's what we're going to work towards. But before I talk about that, I just want to talk about the test pyramid, right? So that's a set of testing strategies for microservices, and I can't stress, too much the importance of automated testing. I really believe that is the sort of the foundation of modern software delivery, right? Automated tests are fast, reliable, scalable, much better than using humans for it. You want to have fast tests because that accelerates the deployment pipeline. It actually accelerates the edit, build, test micro sort of workflow that we do many times a day. And that will go a whole lot faster if you can quickly execute some unit tests. You could also use test-driven development to write new code much more easily. And then when you're modifying legacy code, code that someone else wrote or code that you wrote last week and can't remember how it works, the tests act as a safety net so that you can do it quite confidently. So that's all pretty basic stuff, but sadly, a lot of organizations still struggle with this. They're still relying on QA to actually do the testing. So the idea with the test pyramid is that it sort of defines the testing strategy. It defines the types of tests that you should write and their relative proportions. And it's sort of modeled after the food pyramid, which apparently was not actually a very scientifically sound idea. And in many ways, this test pyramid is not a perfect metaphor for the test strategy that you should follow. except for the fact that I think a really key idea with the test pyramid is the tests at the bottom, they actually run in memory. So they are reliable, they are fast, incredibly fast, and they're very cheap to write. And then as you move up the test pyramid, the tests actually get more brittle, they can be flaky, they slow down because they're more heavyweight, they involve the database, the network, and so on. And they tend to be a lot more complex. And I think it's really important to try and push tests as far down the pyramid as possible in order to shorten the feedback loop. So if you've got some algorithm, you really want to test that using unit tests and not some higher level test that's using the database, because that will just run orders of magnitude slower. And if there's also the possibility of end-to-end testing where you're launching multiple services, and that's even more brittle, more slow, and more complex. And that is really actually counter to the independent deployability principle of the microservice architecture. So that's not actually something that you should even be doing. I'm just going to quickly walk through the different levels of the test pyramid, starting at the bottom with unit testing. So this is where you're fundamentally just testing classes, testing their algorithms. You might be using test doubles in the form of like Mockito mock objects in order to eliminate troublesome dependencies and test classes in isolation. And as I said, this is a good place to test algorithms. And one really interesting blog post I came across a few years ago, it's actually quite an old one, kind of outlines a kind of a good kind of decision-making process for deciding what you should actually unit test. And so there's two dimensions to it, right? One is the benefit of unit testing, which is sort of proportional to the non-obviousness of the code. And then the other dimension is the cost of unit testing, which is actually the number of dependencies that some piece of code has. The idea is you'd have to mock them in order to unit test them. And ideally, what you should be focused on is the top left quadrant, your algorithms. The code that is non-obvious and is also relatively cheap to test. But then you also have in the top right quadrant code that would actually benefit from unit testing, but would actually be difficult to test because of its sort of tangled dependencies. And the recommendation there is that you actually refactor that code, split it into two parts, coordination logic that is not worth testing, and the algorithm, the parts of it that should be tested. And it's a really worthwhile article. I encourage everyone to read that. Here's a quick example, right? This is just some test for the customer entity in the example application. And it's just some basic unit tests that are verifying that the logic for managing available credit works, right? Totally basic stuff. So the next level up is a little bit more interesting. So this is integration testing. But there's I'm using a particular definition that might be different from other definitions. So the goal of integration testing is to verify the behavior of a service's adapters. So these are classes that handle communication between the service and the world outside of the service. So you have adapters like HTTP controllers that handle inbound requests. You have an adapter like a database access object that actually makes outbound requests. So these are the classes on the edge that you want to test to verify that they are sort of properly communicating. And there's a couple of different strategies that you would use here. So if you have adapters that are communicating with infrastructure services, so we've got a picture of a service here. So like you have data access objects, right? And you'd say have classes that are interacting with the message broker. the testing strategy that you would use is you would actually launch a database or launch a message broker as part of the test, and then invoke that adapter and make sure that it's interacting correctly with that external infrastructure service. So here's an example of that. So this is a test case for a customer repository. So the application is using Spring Data for JPA repositories. And this test is using test containers, popular testing framework, to actually provision a database. So you don't have to have one pre-installed. It just runs a Docker container. And then just uses the @dynamic property source to set the right properties in the application context so the data source can connect to it. And then there's just sort of basic tests about saving and loading persistent entities. So that's a good example of this kind of infrastructure service, or the infrastructure adapter test. Now, there are some issues with it, right? Like, on the one hand, this is super good because it's a very focused test on this particular class, and that's quite straightforward versus actually testing it indirectly via the service's REST API. I mean, the downside is that launching containers is relatively time-consuming. Perhaps not so much on sort of a high-powered MacBook, but I've noticed like in a lot of the cloud sort of CI, CD services, those servers tend to be a little slow, and so they take a while to provision containers. So there are a few things you can do to speed things up, like reuse already running containers. And then I've also found a useful design technique is to put each adapter in its own module or Gradle sub-project, so that a change to one adapter won't actually cause another adapter to be rebuilt and retested. So if I'm working on the REST API, that is not going to impact persistence, because there's no actual, that one does not depend on the other. So that's one useful thing to do, is just organize your code to minimize build time dependencies. Then the other kind of adapter are adapters that handle inter-service communication. So say if you have a service that handles REST API, REST requests from some other service, or makes REST requests to some other service, or uses messaging to accomplish the same thing, right? That actually needs testing, but specifically what you almost always need to use is consumer-driven contract testing. So that's a testing technique where you test two services that ordinarily communicate in isolation in a way that verifies, that validates that they actually can communicate. And it relies on sort of these contracts. So here's an example of that. So imagine, like in this application, API gateway is forwarding a post request to the customer service in order to create a customer. And there's two classes involved in that. In the API gateway, there is a customer service proxy that's just wrapping the HTTP client. And in the customer service, there's a controller that is handling the request. So we need to write tests for those two classes that run in each service's deployment pipeline that ensure that they can communicate. And that's done by, if you'd like in this example, I'm using Spring Cloud Contract. I write these, the consumer team, the API gateway team, write these contracts, which are example HTTP request response pairs that actually define the API gateway's view on what the customer services API looks like. And then there's a sort of kind of a workflow. They're actually written by the API gateway team, given to the customer service team, who then publish them so that the API gateway team can use them in their deployment pipeline. And then the customer service tests, customer service proxy tests, use those contracts to configure a WireMock server to simulate the behavior of the customer service API. And then the customer controller tests also use those contracts. The tests for each contract, there's a test case which sends in the requests, the contract's request, and then verifies that the response that comes back matches the contract's response. And it's like, well, if they're both parties are tested with the same contract, well, fingers crossed, they must be able to communicate, right? But we're actually avoiding all of the complexity of testing these two services together. And it also, and it ensures that there are no breaking changes. The downside is that it's extra work, but I think it's much better than the alternative, all right? There's no sort of free lunch here. You'd either write end-to-end tests, which have their own problems, or you write these contract tests. And I think if companies are finding this to be a burden, it's usually because they've got an excessively fine-grained architecture with lots of unstable APIs, and so they're constantly updating these contract tests. So if it's a problem, that's indicative of some deeper architectural issue. Okay, so that's integration tests. Above that, we have component tests, and the goal is you're going at this point, whereas previously we were just testing parts of the service, now we're going to test the whole service. But you don't want to repeat the testing that was done earlier. So maybe these are more like smoke tests where you're just making sure the service starts up and can connect to the various infrastructure services, and you're not really testing it in a super thorough way. And here's an example of a test that's doing this. Once again, it's using test containers to provision all of the services, infrastructure services, Postgres, Kafka, Spring Authorization service that this service needs, as well as provision the service itself. And then it's using Rest Assured to test the service's API. So there's a lot going on under the covers, even though the test is sort of fits on a slide. And then, as I said, the level above that is end-to-end testing, but the message is don't do that. That should not be part of your deployment pipeline because it violates one of the key definitions of microservices, and these tests are incredibly brittle, slow, and complex. They just fail at random, and then you have to inspect them to see whether the failure is real or not, and it's sort of very problematic. But there are alternatives. Maybe run end-to-end tests at night. Maybe run them continuously in production. And then I'm going to talk about some testing in production techniques that you can use later on right at the end, where it actually is an alternative way of verifying that everything is working. Okay, so let's move on. Let's talk more about some of the details of building a deployment pipeline that deploys things to Kubernetes. So yeah, this super crude diagram, right? But you can imagine that we've got this deployment pipeline that builds and tests the service, and then it publishes these sort of container image and a Helm chart artifact. And let's say that this is implemented using GitHub Actions, though you could do the same equally as well with like Circle CI or some other equivalent SaaS product for building. So there's multiple steps to this pipeline, right? So the first step is just running Gradle build, no big deal. One interesting thing is though that you want, say with Gradle, you want all of the fast running tests for all of the sub-projects to execute before any of the slower running tests. And so you might need to use constructs like must run after to ensure the proper sequencing. I found that's useful. But that's the basic thing, right? Nothing else to say there. So ultimately, the key thing we're doing here is building the Docker image. And that's fairly straightforward. You write a Docker file, and then you, in this case, I'm running docker build x build, which builds a multi-architecture. image. Kind of ran into this when I got my M1 MacBook a couple of years ago, right? Suddenly it was like, Intel architecture in the cloud, ARM on my laptop, and things weren't working. So it's useful to build multi-architecture images. But the really interesting thing is, to run something on Kubernetes, it's not just a container image. You need a whole bunch of YAML files to do that, right? You need these manifests. So in particular, you need a deployment manifest that tells the Kubernetes how to run the containers. I mean, there's a whole bunch of other details there, right? You'd also need you typically need a service manifest to configure a service, which is a load balance, domain name, and virtual IP address. And then if this service is handling external traffic, you might need an ingress resource to configure an external load balancer to like route into the cluster. So it's YAML, 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 right? You need that too. And then also, the other tricky thing is the YAML might have values that's environment specific, like the host name of the database, right? This is all relates to Spring externalized configuration. That is going to be different in different environments. So it's like, well, how are we going to do that with YAML? So one solution is to use a Helm chart, which is, Helm is a package manager for Kubernetes. And a Helm chart is basically a bunch of templated or parameterized manifest files. So a bunch of YAML with placeholders. And to me, it's an interesting templating language. I think it's based on Go, and I find it a little bit bizarre. And it suffers from all of the usual problems, I think, of having an embedded DSL instead of, or a DSL instead of a real programming language. But it's sort of workable, right? And so like there on the screen, there's like an excerpt from the deployment YAML that points to the container image. And then there sets up the environment variables for, well-known Spring configuration properties. And there's detail. I mean, it ends up getting packaged as a tar file and put somewhere, but that's a detail. And then when you want to use a Helm chart, you can just go Helm upgrade-install, specify the Helm chart, and then you can specify the values. And those get substituted into the templates, and a bunch of YAML files are generated, which are then passed into Kubernetes. So it's workable. It's not the most pleasant thing, like a lot of Kubernetes configuration. It's funny, as an aside, I always used to kind of get negative about UI development, right? Like, I'm in this Spring world, it's really nice. And then you go into the UI world, and it's like, JavaScript frameworks. And then I went into the DevOps world, and it's, YAML, tools that begin with K. And a bit frustrating, but that's just the life of a professional developer, right? Okay, back to this. So, you've got a Helm chart. It makes sense to test it. And one really interesting way to test it is actually to spin up a Kubernetes cluster locally in your build pipeline or on your laptop. And I use a tool called Kubernetes in Docker, which actually runs Kubernetes inside a Docker container. And then once you have it running, you can install the Helm chart. It's kind of cool in a way. I don't have to have a pre-provisioned Kubernetes cluster anywhere. Downside, though, is that it's kind of heavyweight because you've got to download actually, you have to, in the CI, you have to install kind. You have to download the kind image. You've got to start up the cluster, and then you've got to perhaps pull down various container images as well, and that can be a little slow. But you can optimize it to actually use like a Gradle incremental task to only run the tests when the chart changes. That's a useful optimization. And then you can use a local container registry as a cache of locally loaded container images, so the Kubernetes cluster isn't continuously pulling them down from the internet. and that can help. But then the other really interesting thing that you can do is before even actually testing the Helm chart by installing it, you can actually test the YAML that is generated by the Helm chart. And that's really useful, right? So, because you can run the command Helm template, it just spits out a bunch of YAML documents. So you can make assertions about that. And one really handy way of, almost said groovy way of doing it, is to use Groovy plus Spock, the Spock testing framework, to write these kinds of tests. So the when section actually uses Helm template to actually run Helm, parses the YAML, gets back basically a map of, an untyped map. And then all of the cool sort of groovy dynamic features let you navigate through that map and then make assertions about the values of certain properties in that map. And it's kind of nice, right? And you actually can run this before investing the time in running the heavier weight test that actually spins up a Kubernetes cluster. Because if you've got a typo, even if you have a typo, if you have a typo in your YAML files, this will quickly fail, right? So you're getting fast feedback. Rather, you don't have to wait for the kind cluster to spin up, and then eventually for things to fail. Really, really useful. So yeah, assuming that your Helm chart then passes the test, the last thing you need to do, at least at this stage, is publish the image and the Helm chart that references the image to a container registry. And that's just running a build command and running a couple of Helm commands to package the Helm chart as a tar file and then push it into the container registry. So that's the final step of the, in this case, the GitHub Actions workflow. So then the next step is, well, okay, so the new version of the Helm chart is in this registry. How do we go and install it into our production environment? And I guess the thing you don't want to do, of course, is just manually type in some command, right? Helm upgrade -- version, new version. You could do that, but that's manual. It's not reproducible. And it's, we don't do that anymore. So the right approach is to use, one possible approach, which I think is quite good, is to use GitOps-based deployment, where you have a Git repository that specifies the desired state of the cluster, the particular versions of all of the Helm charts that you want to install, plus actually other manifests as well, but though here I'm focusing on the Helm charts. And that's quite good, right? The Git repository is the state of your cluster, which means it's reproducible. Git is your UI, so if you want to roll out a new version, that's git commit push. If you want to revert back to a previous version, that's git revert push. And then also, which is really, really good, the git commit log is a history, or commit history, is a log of all of the changes. It's an audit log of who changed what and when. So if there's an outage, you just go look in the git commit history to see what's changed recently. So super useful. Okay, so how does this work? Well, there's a couple of popular tools out there. One of them is Argo CD, and I'm actually going to talk about Flux CD, which is kind of ironic because the company behind it just announced that they actually have gone out of business. But it's CNCF project, so it will find a home. So I'm not worried about that. And it's really interesting. Flux actually runs inside the Kubernetes cluster. So rather than sort of your deployment pipeline accessing Kubernetes, pushing things into Kubernetes, essentially Flux is pulling things into Kubernetes. So the most basic functionality is that it, when you do a git push to the configuration repository, eventually that will get picked up by Flux, which will then reconcile the state of the cluster with the state of the repository, add and delete, update Kubernetes resources. So it's really, I mean, at this level, it's a very sort of basic yet effective mechanism. You want to deploy something, do a git commit to the configuration repository. And then Flux takes care of the rest. So like the way you actually install a Helm chart with Flux is that there is a Helm release manifest that basically specifies the chart name, the repository where you can find it, the chart version that you want to install, and the values for that chart. So, you know, it's a very sort of straightforward mechanism. But, you know, you might be thinking, well, it's pretty tedious. Every time I publish a new Helm chart, I have to go edit some manifest file and git commit, git push it. Well, one of the nice features of Flux is that, at least in your dev cluster, it can automatically monitor your container registry for new versions that satisfy certain criteria that you define. So when the deployment pipeline publishes a new version of a Helm chart, Kubernetes, Flux will pick that up. And then what's really cool, it will actually edit the Helm release manifest and actually to put in the new version, do a git commit, git push, and then deploy that change, then apply that change to the Kubernetes cluster. So it automates the otherwise manual editing of the Helm release manifest, which is quite nice. And the way it's there's a bunch of resources that you have to define, and then also the manifest that you want to update actually has this marker comment that's some specially formatted syntax, but that tells Flux where to make the edit, which is pretty nice. Okay, so that's one thing we've got sorted out, right? Like, so at least new Helm chart versions are automatically deployed, at least into the production, at least into the dev environment. And that then leads to the next question is, well, like, how do you support multiple environments? You're probably not going to deploy straight to prod, but you want to deploy to a dev or staging environment. And then there's a couple of sub-problems here, like, you know, each Helm chart will have a different version, one in dev, one in prod. There will be values that are different in each environment. And then also, let's say once you've successfully deployed a new version in dev, you want to update prod with that new version. How do you propagate that change in a fairly sort of straightforward and reliable way? So there's multiple parts to the solution. One of them is to use this tool Customize, which is its purpose in life is to tailor Kubernetes manifest to a particular environment. So you define a base customization, which is a directory containing those manifests. And there's some customize.yaml file in there as well, but that's, in this point, that's kind of not too important. It just has to be there. And then for each environment, you define an overlay customization. Another directory, one for dev, one for prod, that has a Kubernetes, that has a customize.yaml file in it that specifies that the base is is actually the app/base directory. And so that's the first thing. And then each of those overlays can have extra manifests in them that are environment specific. Like the dev one could have the manifest that configure automated version updates. But then the really interesting part is that these overlays can have patches, which are files that modify the manifests in the base. And then the Kubernetes dev cluster will reference the dev overlay, and the Kubernetes prod cluster will reference the prod overlay. Now, here's an example of patching, right? So there's the manifest that's getting patched in base, and then there are the two patches, one per environment. And you can see that they've got slightly different values, and there's an algorithm for sort of defining how the patch is actually applied to the base manifest. So quite a useful mechanism. And so that's a way of having kind of eliminating copy and paste, but then tailoring the manifest to a particular environment. So it's kind of weird, like in the Helm charts, it's actually templating, but then in these Helm releases, we're actually patching. And sort of a feature of customizes, it says, tailor manifest without them being templated. So it's like different parts of the ecosystem work in a different way. Then the last part is, okay, we made a change. We've successfully installed the Helm release in the dev environment. How do we get that into production? Well, we can simply do that using this notification mechanism that Flux provides. You can arrange for it to trigger a GitHub action when a Helm chart is successfully installed that can run the tests, could potentially run tests. But then what's really interesting, it can actually edit the production patch with the new version and commit that, do a git commit, git push, which then triggers the deployment in the production environment. So you get this automatic promotion mechanism, which I think is super interesting. Okay, so now we've sort of initiated the deployment into the production environment. So the very last thing I want to mention super briefly is to actually increase safety and to prevent you from breaking production. You can actually use canary deployments, where you can deploy the new version into production, but don't route production traffic to it, test it, and then gradually shift traffic from the old version to the new version while monitoring its behavior. So there's another Flux CD tool called Flagger that actually does this. It works with either ingress controllers or service meshes to do the traffic routing. And it uses something like Prometheus, some monitoring system to figure out whether the newly deployed service is healthy. So you can deploy the new version alongside the old version. Don't route any traffic to it, but maybe test it in some fashion. And then you can incrementally start shifting traffic from the new version to the old version. Gradually ramping up the amount of traffic, right? And then if at any point there's something goes wrong, like there's a spike in latency or a spike in error rates, you could just abort the rollout. And then eventually you're shifting all of the traffic is going to the new version, and you ultimately undeploy the old version. And Flag is a super interesting tool for doing that. Once again, it's configured by a bunch of YAML files, but it seems to work quite well. Anyway, so that's my talk. See the moderator getting nervous. So yeah, big idea, right? Fast automated deployment pipeline really is essential, right? It improves developer experience. And just overall productivity. You actually have to push tests down the test pyramid. You need to avoid any form of end-to-end testing in a microservice environment. And then, in terms of mechanics for Kubernetes, your deployment pipeline is publishing Helm charts. You're going to use GitOps style deployment. And I'd highly recommend using canary releases to safely update production. So that's my talk. Hope you found it useful. And thank you for listening.
Thank you, Chris. I think the there is a coffee break right now, so I think we have some time to ask the questions, if any. I hope so. Can I probably just start with my question then? It's easy to deploy the stateless services, right? But when it comes to deploying the stateful services that access the database, it's always a question, how do we automatically roll out the database schema changes? Any hints how to do this?
Oh, so you're not really rolling out the database itself, but you're actually doing schema updates, right?
Yes, exactly.
I mean, you know what I've been doing with the services that I've been implementing, I've been using Flyway for just applying the changes. So when you deploy a new version of the service, that will do the schema migration at that point. And I think that's kind of a really simple, effective approach, right? But I think there might be times when you want to do a large-scale schema migration, and so perhaps you might end up decoupling the code deployment from the schema migration and doing the schema migration first.
Exactly. It's exceptionally in the case if you want to do like a canary release and not immediately replace all the replicas with the new version, so you need to keep two of them running. It's basically...
Yeah, you know, I guess it's sort of implicit in what I was saying is any schema migration has to sort of be, it would be backwards compatible. So it's always because I feel like you don't shut the world down, right? You always have old versions of the new service running along new versions of the service. And so the schema has to support both, which I think is, I mean, it can be tricky, right, to figure out the sequence of migrations to get from A to B. You can't always take the direct route. But that's, to me, is the nature of modern software that does not have maintenance windows.
Thank you. Who was next?
Thanks for the excellent talk. Not a question, really, but more of a suggestion. I had the same experience when I started trying to deploy my services to Kubernetes. It was death by 1,000 YAMLs. But I had really good experience with Pulumi. It's a infrastructure as a code tool where you can use like any programming language.
Oh, was that Pulumi?
Pulumi, yes.
Oh yeah, I haven't looked into that, but it would be consistent with what I said, that we should be programming in real languages and not these half-baked attempts at...
Yeah, exactly.
Yeah.
So, I suggest you should maybe give it another look. It's a really better experience than using YAMLs.
Yeah, cool. Thanks. I will.